Wave energy conversion is a promising renewable energy technology that harnesses the power of ocean waves to generate electricity. As the world moves towards a more sustainable future, ocean wave energy presents a significant opportunity to meet the growing energy demands while reducing carbon emissions. In recent years, significant progress has been made in the development of wave energy conversion technologies, with various systems being designed and deployed in different parts of the world. This innovative technology has the potential to provide a clean, reliable, and consistent source of energy, making it an exciting area of research and development for engineers and scientists. Ocean wave power conversion systems work by converting the kinetic energy of ocean waves into electricity. There are several types of wave energy conversion systems, but most of them use the following basic principles. Capture. The first step in wave energy conversion is capturing the energy of the ocean waves. This is done by using a device that moves with the waves and is connected to a generator. The movement of the device causes the generator to produce electricity. Conversion. Once the energy is captured, it must be converted into usable electricity. This is typically done through a system of hydraulic pistons, gears, and other mechanical components that amplify and transmit the motion of the waves to the generator. Transmission. The electricity generated by the system is then transmitted to an onshore substation or offshore platform via underwater cables. From there, it can be distributed to homes and businesses. The design of wave energy conversion systems varies depending on the specific technology used. Some systems use buoys or other floating devices that move up and down with the waves, while others use underwater turbines that are driven by the motion of the waves. Overall, wave energy conversion systems have the potential to provide a consistent, renewable source of electricity with minimal environmental impact. There are several types of ocean wave power conversion systems, each with its unique design and method of harnessing wave energy. Some of the most common types of wave energy conversion systems include oscillating water column, OWC. An OWC system uses a partially submerged chamber to capture and compress air as waves enter and exit the chamber. The compressed air is then used to power a turbine, which generates electricity. Point absorber. A point absorber system consists of a floating buoy that is attached to an underwater generator. The buoy moves up and down with the waves, which drives a piston that powers the generator. Attenuator. An attenuator system uses a series of interconnected, floating segments that move with the waves. As the segments move, they drive hydraulic pumps that generate electricity. Overtopping. An overtopping system uses a ramp or reservoir to capture the energy of waves as they break over the top of the structure. The captured water is then released into a turbine, which generates electricity. Oscillating wave surge converter, OWSC. An OWSC system uses a hinged flap that moves back and forth as waves pass over it. The motion of the flap drives a hydraulic pump that generates electricity. Floating oscillating water column, FOWC. A FOWC system is similar to an OWC system, but it uses a floating structure that is anchored to the seafloor. The floating structure moves up and down with the waves, compressing air that powers a turbine to generate electricity. Submerged pressure differential, SPD. An SPD system uses a submerged, hollow cylinder that is open at the bottom. As waves pass over the cylinder, the pressure difference between the top and bottom of the cylinder drives a turbine to generate electricity. Several factors influence the design and efficiency of an ocean wave power conversion system, including wave climate. The characteristics of the local wave climate, such as wave height, period, and direction, are crucial in determining the most suitable type of wave energy conversion technology to be used. Site characteristics. The site conditions, such as water depth, seabed topography, and distance from the shore, also affect the design and efficiency of the system. For example, some systems are designed for shallow waters, while others are more suitable for deep-sea locations. Device size and weight. The size and weight of the wave energy conversion device are important factors that affect the cost, installation, and maintenance of the system. Larger devices typically generate more power but may be more expensive and difficult to install. Power output. The amount of power that a wave energy conversion system can generate is influenced by the technology used, the efficiency of the energy conversion process, and the local wave conditions. The power output should be sufficient to meet the needs of the intended application. Reliability and maintenance. The reliability and maintenance requirements of a wave energy conversion system are critical factors in determining the system's overall efficiency. A system that requires frequent repairs or maintenance can increase costs and reduce its effectiveness. Environmental impact. The potential environmental impact of a wave energy conversion system must also be considered in the design process. For example, the device's impact on marine life, the seabed, and the surrounding ecosystem must be carefully evaluated. Cost. The cost of the wave energy conversion system, including installation, maintenance, and operation, is a significant factor in determining the system's feasibility. The cost must be competitive with other renewable energy technologies and conventional power sources to be economically viable. How is energy captured from ocean waves and converted into usable electricity? Energy is captured from ocean waves and converted into usable electricity through a process that involves several steps. Here's a general overview. Wave motion. The motion of ocean waves generates kinetic energy. Energy capture. A wave energy conversion device captures the kinetic energy of the waves using a variety of methods, depending on the type of technology used. Some systems use floating devices that move up and down with the waves, while others use submerged or partially submerged structures. Energy transfer. The captured energy is transferred to a generator that converts the mechanical energy into electrical energy. The generator is usually connected to the wave energy conversion device through a system of hydraulic pistons, gears, and other mechanical components. Power conditioning. The electrical energy generated by the system is typically in the form of AC voltage, but it needs to be conditioned to match the requirements of the electricity grid. This is done using power electronics, which convert the AC voltage to DC voltage, regulate the voltage and frequency, and control the power output of the system. Grid connection. The conditioned electrical energy is then transmitted to the grid using underwater cables. The energy can be used directly by local communities or stored in batteries for later use. What are the advantages and disadvantages of ocean wave power conversion systems compared to other renewable energy sources? Like any renewable energy source, ocean wave power conversion systems have their advantages and disadvantages when compared to other renewable energy sources. Here are some of the main ones. Advantages. Predictable and consistent. Ocean waves are more predictable and consistent than other renewable energy sources like solar and wind power, which can fluctuate based on weather conditions. High energy density. Ocean waves have a high energy density, meaning that they contain a lot of energy in a small space, making them a potentially efficient source of power. Minimal visual impact. Unlike wind turbines or solar panels, wave energy conversion devices are typically located offshore and have minimal visual impact on the surrounding landscape. Little land use required. Wave energy conversion systems do not require large areas of land, making them suitable for densely populated areas where land is limited. Scalable. Wave energy conversion systems can be scaled up or down to meet different energy demands. Disadvantages. High upfront costs. The cost of designing, building, and installing ocean wave energy conversion systems is typically higher than other renewable energy technologies, which can be a barrier to widespread adoption. Limited commercial deployment. Compared to other renewable energy technologies, ocean wave energy conversion systems are not yet widely deployed on a commercial scale, which means that there is limited operational experience and a lack of established supply chains. Limited availability. Ocean wave energy conversion systems are only viable in areas with sufficient wave energy, which limits their availability to certain locations. Environmental impact. As with any infrastructure project, Ocean wave energy conversion systems can have an environmental impact, including on marine ecosystems, wildlife, and habitat. Maintenance and repair. Ocean wave energy conversion systems can be difficult to maintain and repair because they are located offshore and are subject to harsh ocean conditions, which can increase operating costs.